Hello, I'm Joshua Weaver and this is my presentation on the Edmonds-Karp algorithm for finding the maximum flow for ECM3428 algorithms that change the world. Network flow problems are a class of problems that involve optimizing the movement of resources through a network. Whether it's data transfer between devices or managing urban traffic, the challenges are vast and varied. Algorithms are crucial to solving these problems, and one such algorithm, called the Edmonds-Karp, addresses the task of finding the maximum flow. This involves minimizing the cost associated with moving resources from a starting node to an end node. Firstly, to comprehend the Edmonds-Karp algorithm, it's important to understand directed graphs. Directed graphs consist of nodes and edges, representing one-way connections between nodes. Flow networks, a type of directed graph, control the movement of quantities between nodes. Unlike general directed graphs, flow networks adhere to flow conservation, ensuring that the total incoming flow equals the total outgoing flow at intermediate nodes. The max flow problem in flow networks seeks to optimize the flow from a source to a sink, adhering to edge capacities. Before discussing the Edmonds-Karp algorithm, understanding the Ford-Fulkerson algorithm is essential. The Ford-Fulkerson algorithm addresses maximum flow problems repeatedly, identifying augmenting paths within the residual graph. This graph is formed by subtracting the existing flow from edge capacities. The algorithm enhances the flow along the augmenting path by the maximum obtainable quantity, determined by the minimum capacity among traversed edges. The Edmonds-Karp algorithm is an optimized version of Ford-Fulkerson, effectively tackling the max flow problem. The key improvement lies in the selection of augmenting paths. Edmonds-Karp employs breadth-first search to identify the shortest paths systematically during the intermediate stages. Augmenting paths define pathways with the capacity for additional flow. The use of BFS ensures a consistent preference for the shortest path from source to sink when faced with multiple augmenting paths. This systematic approach enhances the algorithm's dependability, termination assurance, and overall efficiency. The Edmonds-Karp algorithm is crucial for solving real-world network flow issues, optimizing resource use in communication and transportation. It helps industries run more smoothly in various critical domains too, such as airlines and power systems. The algorithm's clever use of breadth-first search makes it a vital tool for simplifying complex network challenges. This is my Python implementation that demonstrates the design and functionality of the Edmonds-Karp algorithm. On lines 1 to 4, it begins by importing essential libraries. These are deque for double-ended queue operations, networkx for graph manipulations, and matplotlib.pyplot for graph visualization. The initializeEmpty matrix function, defined on line 7, prepares the canvas for the algorithm's execution. This function creates an empty matrix based on the given rows and columns. Its significance lies in initializing the flow matrix F, a key data structure that tracks the flow of resources across the graph. The flow matrix is important for recording the amount of flow on each edge and is crucial in updating the network during the algorithm's execution. The has-negative cycle function, defined on line 16, performs a check for negative cycles in the graph. By employing a distance relaxation mechanism, this function iterates through the graph, ensuring the absence of negative cycles. Detecting negative cycles is a fundamental step for maintaining the correctness of the algorithm, ensuring reliable convergence. Similarly, the has-non-intercapacity function, down here, defined on line 45, scans the graph for non-integer capacities. This check on the input graph adds a layer of validation, ensuring that the algorithm operates on a graph with well-defined and realistic capacities. Such validation steps are essential to prevent unexpected behavior and ensure the algorithm's robustness. The algorithm is encapsulated in the Edmonds-Karp function, defined on line 86. This function initiates the maximum flow at 0 and sets up an empty flow matrix. Before proceeding with the main loop, the algorithm checks for negative cycles and non-integer capacities, ensuring a valid input graph for further processing. Inside the loop, the algorithm employs breadth-first search to systematically identify augmenting paths. The BFS ensures a consistent preference for the shortest paths from the source to the sink. The identified augmenting paths guide the algorithm in updating the flow matrix and, consequently, the maximum flow. The code concludes with an example usage on lines 134 to 167, showcasing how to apply the Edmonds-Karp algorithm to a specific flow network represented by capacity and edge matrices. Finally, the maximum flow is then printed for clarity by the visualization function. Here is the output. Augmenting paths are strategically identified to optimize the flow from the source node 0 to the sink node 9. The algorithm determines that the maximum flow in the network is 4, where the bottleneck is clearly seen. This result reflects the algorithm's ability in calculating the maximum flow.